Hello, welcome to this webinar meeting. This is Roland Caulcutt, I'm the Chairman. I'm Vice Chairman of the Quality Improvement section of the Royal Statistical Society. I'm the first speaker as well as the Chairman, so I'm going to talk about measurement error in general terms using no mathematics and very little statistics. I'm sure you'll cope with that. The second speaker, Martin Gibson, after I've spoken for 20 minutes, he will go into more detail on the AIAG approach to measurement systems analysis. We all have considerable experience in many industries discussing measurement error. Well, after the speakers, we will have time for questions, probably about 25 minutes. Some of you may have already downloaded the PowerPoint presentations and may not be viewing the slides as they are presented. Each presenter will keep you informed of the number of the slide he is showing. So, measurement error. I'm going to talk about two processes. This is a production process. It produces products and or services. The inputs include materials, information, etc. If we want to assess the performance of this process, then we need to measure at least what is coming out of it. So we put product or service into a measurement process. That's a separate process, and from that we get data. The data, of course, we hope will help us to assess the performance of the production process. So I'm going to be talking about two processes. Hopefully you'll realize which one at any moment. A process, in my opinion, is a combination of equipment, people and procedures that work together to produce products and services. All of the data coming from measurement processes, of course, is also data coming from the past. Right, measurement error. There are, believe it or not, people who wish to believe that measurement error does not exist. These people measure something once and assume the measurement is correct. They would say it's absolutely pointless taking a second measurement. Well, let's see what does happen when we take a second measurement. A very simple situation, we are measuring the length of a component, and it's in centimetres. That's our first measurement, slightly over 16 centimetres. If we do take a second measurement, it doesn't surprise me that the two are different. The person who doesn't believe in measurement error would probably say, well, one of these is correct and the other is wrong. And though he wouldn't say it, he probably thinks the one that is wrong because of a person doing something wrong. Of course, he wouldn't know which of these two is the right one and which is the wrong one. Let's have some more. When we measure more and more of these, I don't know quite how the person who doesn't believe in measurement error is going to cope with this. I suggest we cope with this by measuring the spread of the measurements. Remember, we are measuring the same component repeatedly. So this is not variation in the component, it's variation within the measurement process. And clearly the spread of the data is telling us something about the measurement process. It's indicating the precision of the measurement process. The bigger the spread, the worse the precision. Now, precision can be spoken of in several ways. We could measure the spread using the range of the data. That's subtracting the smallest measurement from the largest. That's the simple way to do it, but we actually don't do that. We put the data into a computer or a calculator and we measure something called a standard deviation. The bigger the spread, the bigger the standard deviation. You don't need to know what it is, but we multiply that by 6 and we get this. The blue line is longer than the red one. The red line indicates the spread of the actual data. The blue line indicates a bigger spread. That's an estimate of the spread we would perhaps get if we took many, many measurements. So that's looking to the future. Now, precision has associated with it quite a lot of jargon. If the measurements were made by the same person using the same equipment at roughly the same time, then we refer to that spread as repeatability. This word has been around for hundreds of years and it's used in many industries. Now, if the measurements were made by different people, perhaps in different places, using different equipment and at different times, we would refer to that as reproducibility or perhaps R&R. It depends which industry you're in. Now, there shouldn't be confusion about these definitions because there is a document known as the VIM, published by the International Standards Institute. It's the International Vocabulary of Metrology, and it defines repeatability and reproducibility. It could be simpler, it's a bit circuitous, but the definitions are there. And if everyone adopted these definitions, then there wouldn't be any confusion. But I know from practice that in some industries, especially where engineers manufacture components for automotive, they do stick to these definitions. But in the chemical industry, where I have a lot of experience, people use repeatability and reproducibility as they have for hundreds of years. And they are very interested in any differences in measurement that might exist if the producer measures the product and the consumer measures the product, or the customer. This is extremely important because often the price paid by the customer to the producer depends on these measurements. And if the two measurements don't agree, then there has to be a dispute and maybe some action taken. If the difference between the measurements is small, then okay, perhaps we take the mean. Right, now we have a number for repeatability. We have a number for reproducibility. All of these are in centimetres. The measurements are in centimetres, the mean or average is in centimetres, the standard deviation is in centimetres, and so are repeatability and reproducibility. But what does the number mean? To make it more meaningful, you really need to compare the repeatability and reproducibility with something else in the real world. And what you do depends on the purpose of measuring. Perhaps you're measuring in order to control a production process. Perhaps you're measuring in order to assess the capability of a production process. Perhaps you're measuring in order to improve a production process, etc. So what you do with repeatability and reproducibility now depends on your purpose. Let us focus on someone who is trying to classify product. Of course, the product measurements need to lie with it between the specification limits. But the measurements we have on the product are inflated in various ways by the measurement error. So it's reasonable to compare repeatability and reproducibility with the specification and express it as a percentage and hope that the percentage is small. On the other hand, if your purpose of measurement is to improve the process, then it's reasonable to compare the spread of your repeat measurements with the spread of the real product variation. Alternatively, you can calculate something called number of distinct categories, which perhaps the second speaker will elaborate on. Now, if an auditor is doing this to you, he or she may say, your process, your measurement process, is perfectly capable of correctly classifying product, but it is not capable of improving the process. And you may pass on one and fail on the other. And I think Martin is going to elaborate on that. Now, I'm running out of time, so I'm just going to skip this. But these beautiful purple measurements are shrouded in uncertainty. Because of measurement error, the green and the red measurements are understandable, but there's doubt about the purple measurements, whether the product is good or bad. So that spread, that band of uncertainty, needs to be small compared with the width of the specification. Ideally, the spread needs to be less than 10% of the specification. Now, there is another document published by the International Standards Institute which should also eliminate the differences in terminology that exist between different industries. It's known as the GUM, the Guide to the Expression of Uncertainty in Measurement. Imagine that we take one measurement. If we simply quote that one measurement, the only thing we can be sure of is that it'll be wrong, maybe only slightly wrong. It's much more useful to quote the measurement plus or minus something as what is known as a confidence interval. So you need, again, one of these standard deviations that you would get from an experiment in which you are repeatedly measuring the same item. So that is recommended by the GUM. That, I think, is growing in popularity. Now, one final slide just to upset everyone. We've been talking about precision. All these documents I've quoted and the ones that are coming in the next presentation talk at great length about precision of test methods. They hardly mention, and perhaps completely ignore, bias. Those are the 11 measurements we had. Suppose that is the true value, which we could get by some other means. This is clearly not a good measurement process because it is biased. And in practice, bias could be a bigger problem than precision. But we probably won't mention bias again. Right. Thank you very much for your attention. I'd now like to pass you over to the second speaker, Martin. Over to you, Martin.
Yes, thank you, Roland. Good afternoon, everybody. Martin Gibson here. So I've been involved in measurement systems analysis and gauge repeatability and reproducibility for over 20 years now, primarily with automotive and other industries. And I think some of the points that Roland was picking up on, defining repeatability and reproducibility, I will go into. And I want to ask a series of questions as I bring my slides forward, because I think there are some issues. These issues have become aware to me over the last few years in some work I've been doing. And it's revolving around auditors, and it's revolving around the interpretation of TS 16949, and then how that fits in with the Automotive Industry Action Group Measurement Systems Analysis. I would ask you, please, as I'm going through my presentation, to refer back to the original questions on the flyer that was sent out, and just to quickly go through it, because that is my second slide. Do you know, who you're working with in your organisations, do you know how accurate and precise your measurement and test equipment are? And do you sometimes think that the work is condemned as bad simply because of uncertainty? And that's what Roland was alluding to in his presentation. And how good are your measurement systems? Do you truly understand measurement system uncertainty within your organisations? And does your auditor share that? What knowledge do they have, and what can you do about it? I want you to think about those questions, please, and then I want to raise some more based on the experiences I've been going through the last few years. So on slide 3, I thought it was probably better to start with an extract from TS 16949 under 7.6.1 Measurement Systems Analysis. And in fact, this is under review within the ISO community to maybe merge it into ISO 9000 for in addition to come out next year, ISO 9000 2015. And there are some issues within ISO 9000 at the moment because the words variation and measurement don't seem to really exist. But in the clause for measurement systems analysis, it starts off, as you'll see on the slide, statistical studies shall be conducted to analyse the variation. It applies to measurement systems in the control plan. So naturally, we led straight to a manufacturing situation, a production situation, as Roland was describing. However, in my mind, measurement systems apply to anything that you measure. The analytical methods and acceptance criteria used shall conform to those in customer reference manuals on MSA. And other methods and criteria may be used, but the questions that arise first of all, what is the operational definition of statistical studies? And do the organisations, the auditors, the quality managers, understand these studies? And specifically, I was doing some research recently, and it's been confirmed by an actual event. The auditor's response in examining this clause in an audit of an organisation said, can you show me the gauge repeatability and reproducibility studies for each type of measuring and test equipment referenced in the control plan? So those are my first 3 questions. Why are we being led down this gauge R&R path when we have MSA? And in fact, on a recent webinar, I think it was last November, from the Industry Forum, Society of Motor Manufacturers and Traders, common problems found in ISO and TS audits under calibration and MSA was, look at the last 2 bullet points. The MSA is not done for all types of measuring systems, and MSA is only considering gauge R&R. So this is another question. Why is MSA now regarded as being synonymous with gauge repeatability and reproducibility? And I have a suspicion it's possibly due to the influence of the Six Sigma community, who when they teach measurement systems analysis, typically just teach gauge R&R. But mentioning the customer, and let's be fair, everything we do is for the benefits of our customers, and these are the Ford Motor Company MSA requirements from 2009 with regard to this clause on MSA. And it says again, all gauges used for checking shall have a gauge R&R. It leads us directly to gauge R&R, performed in accordance with the methods described by the Auto Industry Action Group, MSA manual, which I have sitting here in front of me. And it's about 200 pages long. And Ford defines that variable gauge studies should utilise 10 parts, measured 3 times by 3 operators, and attribute studies should utilise 50 parts, measured 3 times by 3 in 3 trials. And of course the attribute methodology is what I seem to fondly remember as Kendall's coefficient of concordance, but it's not actually called that and would the auditors understand that? So, are some customers leading the thinking? Why just limited to products? And do you actually know what your customer expectations are? But if we go to the AIAG manual, published on MSA, and it's currently in 4th edition, they do look at everything that you see on the slide. And notice that repeatability and reproducibility is just a small component. I have recently come across 2 professors who say, well, calibration, if your measuring equipment is calibrated, you don't need to do gauge R&R. But the auditors and the standard are looking for it. And I don't think we should forget that what we're trying to do is to distinguish the process variation from our measurement system variation and what the contributions are towards the total observed variation, as lucidly put by Roland. So I want to focus on repeatability and reproducibility because that's really where we are at the moment, and I think the bias, linearity and other issues are being left behind. The manual from AIAG on slide 7 does look at attributes and variables, and it looks at non-replicable data, that's their terminology for destructive testing. But when we have a variable study, and this is some work I'm involved in recently, 10 parts measured by 3 operators 3 times, you're asked to choose parts from 8% of the tolerance band, something again that Roland was speaking about the spread of the data as regard the actual the tolerance of the parts. But be aware that our 10 parts jumps to 90 parts if we're involved with destructive testing. And then the terminology used is a homogeneous batch, but that's a little bit loose. There are 3 basic methods that the AIAG proposed. The range method, very basic with no estimates of R&R. The second method, average and range, seems to have its origins from General Motors in the 60s, but I'm trying to chase that down. And then the third method, again, heavily supported by the Six Sigma community, is to use the ANOVA, or analysis of variance method. And that leads to some more questions in my mind, because I'm working with many engineers, and some very clever engineers with postgraduate degrees, and they still do not understand analysis of variance. It is a new technique to them. So another question is, do organizations, auditors and quality managers actually understand MSA? Do they understand ANOVA? Moving on to slide 8, and now we're getting into the model building part. Cross methods, cross analysis of variance, is when we have 10 parts measured 3 times by 3 operators, and we can investigate interactions. Sorry, it could. So the second one, the nested, as soon as we have destructive testing, where you destroy the part when you test it, it cannot be measured again, either by yourself or another operator. And there is some discussion out in the literature. There's a very good book by Barentine, and all the references are on the final slide of my presentation, so I won't dwell too much on that. But the nested method seems to have arisen, first of all, from Moen, Nolan and Provost, but Bauer and Doug Montgomery, as co-author, wrote a book a few years ago, and they're saying, well, actually, do we need to bother with the nested model? But again, my question is, do the auditors understand nested models? Do they understand analysis of variance? And then we're into another debate. As soon as we start using these analysis of variance models, do we have fixed or mixed effects? It seems to be that many software packages assume a fixed effect. But if our operators are the only operators involved in the measurement system, we could regard those as fixed. But if there is a subset of many operators who could use the measurement system, then that would be random. And there is a debate, and in fact, to my cost, I've found that there is a difference in estimating reproducibility, which we don't have time to go through here. But the software, certainly Minitab version 16 and above, includes fixed, mixed, and they've gone another step further, talking about enhanced models, but they don't use the pooled standard deviation approach. Another software package, fairly simple, SPC for Excel is fixed effects only. Another software packages, I don't know, maybe you can tell me. So the question is, do these guys understand ANOVA? Moving on to slide 9, I won't spend too long on this, but Roland mentioned these. We can split the gauge repeatability and reproducibility and look at it as a percentage contribution to the total observed process variation using variances, which, as we know, are additive. But then the AIAG look at study variation using standard deviations, which, of course, are not additive. Then they have percent of tolerance. Then they've got another category, the number of distinct categories, which is really measurement scale resolution. And the acceptable criteria are at the bottom. And ideally, you'd like them all to be green. However, there will be many instances where 2 of the 4 metrics might be green, and 1 could be red, and 1 could be yellow, or any combination thereof. So, are the metrics truly understood? Do the auditors understand the metric? In the recent work I've been involved with, reproducibility has been close to 0. In other words, the operators are extremely good at matching each other and within themselves, which is what you want. You want to believe the measurements that they tell you are correct. But the auditor said it is impossible for reproducibility to be close to 0. And that, in my mind, begs the question, does the auditor truly understand? There are some other confusions around when we look at destructive or non-replicable gauge R&Rs. And I think the list on slide 10 should be a good operational definition for any type of measurement systems analysis. And I won't read it through it, you can look at it later on. But that's a standard list of what I'd expect to see. But how often is it actually followed? On slide 11, in that same case study white paper from 2002, I've highlighted the important steps. If the overall process appears to be stable and capable, because that's what we truly want, that's what customers look for from their suppliers and internally in their own control plans, it may not make sense to spend the effort to do a non-replicable study since the overall capability includes measurement error. In fact, there's a footnote on this white paper which says, ironically, the higher the CP or the CPK indices, the capability indices, the poorer your number of distinct categories will be, and I've demonstrated that empirically. And the auditor that I'm aware of actually said, well, no, if you failed the MSA study. Well, actually, they've looked at the gauge R&R analysis, and because the NDC is low, and the guidelines are it has to be greater than 5, I think there's a misunderstanding. So a highly capable process gives you a poor NDC. And I think it's very difficult for a company with good processes, capable processes, to then start produce parts across 8% of the tolerance band. So do these organisations, etc., understand this concept? And indeed, on the AIAG frequently asked questions, there is a response to question number 12, and they say, if your process is stable and capable, the spread of this acceptable process distribution includes your measurement error. There may be no need to study your measurement error from a purely acceptability viewpoint. So I want to finish with some questions, just summarising what we've gone through. What is the operational definition of statistical studies? That's what the TS 16949 clause specifies. This has been interpreted by AIAG. Do organisations, auditors, quality managers understand statistical studies? And why are auditors asking for gauge repeatability and reproducibility studies? And why is measurement systems analysis being regarded as just GR&R? It's clearly not, but that seems to be the intent at the moment. And are some customers leading the thinking? I did show you Ford, but if you go on, if you search on the internet, you will find other customer requirements. You'll find others for GM, mainly automotive. So is it the automotive OEMs that are leading this thinking? But why is MSA limited to products? Because as soon as we have data, we have measurement. If we have measurements, we can understand sources of variability, we can make continuous improvement efforts, and we can drive continuous improvement overall. But it should not just be limited to products. But of course, when the Ford and other customers start talking about control plans, you're naturally led to think about products. And do we truly know what our customer expectations are? Because we should do, and then we can develop our systems and processes within the entirety of the organisation to not only meet but go beyond those customer expectations. And do the organisations understand measurement systems analysis of variance. I doubt it, from what I've seen. When you're working with SMEs up to large corporations, the number of people you can have a meaningful conversation with about analysis of variance, in my mind, is quite limited. Do they understand the differences between crossed and nested models? Are they aware of the debates going on in the last 10 years? Do they understand the differences between fixed and mixed model analysis of variance, the metrics? And is there recognition that a high capability will give a low NDC, so you will naturally fail one of the acceptance criteria of a gauge R&R study? And finally, is MSA just seen as a quality management system requirement, or should MSA be seen as a true part of continuous improvement? And I'm erring on the former. I think it's seen as, oh, we've got an audit coming up, let's make sure we've done a gauge R&R study. That's a very cynical view. It's one that it seems to come to my mind that that's actually true. I think I'll just finish with the references are there on slide 13. They'll all be available on the website afterwards. I have to say that I've read some of Bauer's work, but the one by Burdick, Borough, Montgomery was new to me in the last week or so, Design Analysis of Gauge R&R Studies, published by ASA. That looks like quite a hefty book, and it needs more research. So thank you for your attention. I'll now pass back to Roland and the Chair.
So please feel free, anyone who's listening, to ask a question over the telephone.
Just out of interest to Martin, how often do people actually have a problem with linearity? Because normally I would have thought their measurements are within a certain range of variables, so that you would expect it to be linear within that range.
In my mind, the work I've been doing the last 10, 15 years, linearity is not really discussed. People just jump straight to gauge R&R and ignore the linearity and bias aspects.
But something like Minitab, for example, has a whole section on that, doesn't it? And but when I've looked at it, I haven't found it to be particularly useful, because people usually don't have a problem with it. They know what the range is that they should use their measurement equipment for. Yeah,
no, I agree, and it's not been a prominent feature in my work of the last few years, but it is there in Minitab, and it's all clearly explained in the AIAG manual, but again, I think you might be right and people are not too concerned about it.
I would agree. If you're manufacturing a product and you're getting pretty much what you expect to get, then your product isn't varying over a wide range. But imagine a completely different situation where you have a measurement process in a public analyst laboratory. People are bringing in food samples. Some of them will have very small measurements, some will have much bigger measurements. So some people do have to face a huge range of measurements, but perhaps not in manufacturing.
Right. Thank you.
Thank you, Shirley.
Sarah here. If you've got a measurement and you don't understand what the bias is, how do you test for that? So if you've got a test in which you think there is a bias, where you're not testing the true variability and you get a large range, do you know that it's the bias creating the range, or is it the measurement creating the range?
Well, bias creates a consistent difference away from the true value. Now, some people say this idea of true value is nonsense. I don't think so. It's a very useful concept. But in many situations, you can resort to using a much, much better measurement process to get a good estimate of the true value. And that is what you need to reveal the bias.
Thank you.
And again, I think it's Martin here. I think I would add to that and say, I'd go back to the original measuring equipment manufacturer and see over what operating range the measuring equipment is certified and calibrated to, and look at what the expected bias is going to be for various values. And is the gauge, not thinking about operators at the moment, is the gauge being used for its intended purpose? Is it fit for purpose? And I'd certainly investigate that and then potentially design and analyse some bias studies for that particular gauge, and I would certainly remove all extraneous sources of variability by having that operational definition which I had on that list of bullets, looking at the environment, the temperature, the humidity, etc., and truly understand what my gauge is capable of.
I think the problem we have is that it's very difficult to remove any process variations because it's quite a complicated process.
Could I just add, if the bias is stable, then of course it's not introducing any extra variation. It's just moving the whole distribution across. But if you have a bias that is constantly changing in a random manner, that is a much bigger problem.
Yeah.
The only way to identify that is to find a more precise measurement.
Yes.
Okay.
Which usually costs money.
We're using quite an expensive tool at the minute.
I'm reminded though that I was involved in a study many, many years ago when manufacturing were about to sign off the purchase order for some electronic gauging equipment. I can't give any more detail than that, but there was a substantial investment, and I said, have we done any basic studies? And we hadn't. So when we did that, we found that the electronic equipment was not fit for purpose. And in my mind, there are still some circumstances where people have a perception that if you've got an electronic equipment, it's got to be good. Well, unless you study it, analyse it, design the experiments and truly understand its capability, it may not be fit for purpose. And we should not be raising purchase orders on expensive equipment purely because, it's got to be better than what we currently have. And I've seen that many, many times.
Yes, I think some years ago when digital readouts started to appear, many people thought, all the measurement error is now gone. Well, of course, that's rather silly.
Agreed.
Hi, this is Matt.
Hi, Matt.
I'll weigh in. Okay, so do you have any thoughts about the design of particular gauge R&R studies in terms of the sample size that should be used? There are sort of standard guidelines that people tend to use uncritically. Do you ever go in and actually design an experiment that is larger or smaller than those, or is it always a case of using those standard sample sizes?
It's Martin here. I would, because of the nature of the work that I do, a lot of these people are using what you call the standard sample sizes, 10 by 3 by 3 or 90 parts for destructive, or the attribute studies at least 50 parts. Of course, many people I work with will say, I can't afford that, I want to choose something smaller. But I've never, if you like, gone to the extent of calculating an expected risk in doing that from smaller sample sizes. It's almost like these numbers from AIAG have become fixed in stone, and I think that's what the auditor is picking up on as well. So if you move away from that, then the auditors get unhappy. So personally, I've not designed a study as such to enable that to happen, but I'm aware of working with some engineers and others who've used smaller studies and are then somewhat surprised when they're not getting the results that they might want to see.
Martin referred earlier to an MSA study in which the reproducibility was very small. Now, in the chemical industry, that just doesn't happen. Reproducibility is always bigger. And some laboratories completely fail to produce measurements. I've forgotten why I'm saying that. What was the question?
Sample size.
Ah, yes. So, in the chemical industry, the idea of 10 by 3 by 3 is ridiculous. The guidelines in the chemical industry are that you should have at least 10 laboratories participating. Whereas in AIAG they talk about 2 or 3 operators. Now, of course, in practice you can't always get 10 laboratories, but I've always felt in the AIAG method having only 2 or 3 operators really isn't enough. But where your reproducibility is very low, I guess it is.
Thank you.
There are some guidelines. There's a small chapter in one of the references I've provided, Concepts for R&R Studies by Barenstein, published by ASQ. It seems to me to be a very practical guide to the interpretations of the AIAG manual. And there is a section on planning a study, and also what do we do if the results are unacceptable. It seems to be very much a binary pass-fail situation, and it's not that. It should be about a continuous endeavour to improve what we're doing. And he also has some nice examples for different application areas, but I don't think that the chemical industry is included. Well, I just have one here on the nuclear moisture gauge, so it's worth looking at, I think. Well, there is something on measurements in chemical analysis, so it's worth a quick read of that particular reference.
Martin and I are trotting out these references. Of course, every British standard or international standard costs quite a lot of money. So hopefully you have a good employer.
There's one other thing I would say as well. I didn't include it today, but in preparing for this event today, Germany has, I think it's called the VDA standard, and they have seems to be a contrary view to TS 16949 and the AIAG measurement systems analysis. And I don't know if anybody here has got experience of working with German customers or experience of that particular standard. If they have, I'd be welcome. I'd love to hear it, but it's not something that I've used, but I have scant awareness of it. I'll take that as a no then.
I can ask another question.
Yes.
The work that I'm often asked to do around MSA and gauge R&R type studies is very rarely simple in terms of it's almost always destructive, and is sometimes also attribute based. And I've not been able to find anywhere standard methods that are recommended for the combination of both destructive and attribute-based assessment. And I didn't know if anyone has got any ideas around that. I have some approaches that I've used in the past, but I had to kind of come up with them myself. So are there any standard approaches that are recommended for that situation?
Before Martin gives a long answer, let me give a quick one. Destructive testing is very interesting indeed. I would say if your production process is totally stable, you cannot do MSA. You need instability. I've done a lot of investigation of a lot of processes in many industries, and every time I find that the variation you find in the product depends on the period of time over which it was produced. And if the variation is constant over long periods, then you cannot subgroup your products into homogeneous groups.
Yep, and I've come across that commonly.
Mm-hmm.
I'm not going to give a long answer, quite the contrary. All I'm going to say is that there's something that, nobody's mentioned Don Wheeler, and he doesn't like the AIAG approach at all. He uses SPC charts, and that's a segue from Roland. I think that, but one thing he does say is that the purpose of analysis is insight. And I think it's, what is an organisation trying to do? It's trying to demonstrate that they have a stable, capable process. Whether they need to employ gauge R&R, MSA, that's up to them, but if they're well inside the specs and they're meeting custom requirements, then do they actually need to undertake MSA studies? Look at calibration, look at all the traditional things, and then just prove that they've got evidence and data to back it up, and they are insightful about their particular processes. But then, of course, it comes down to understanding their custom requirements, and it comes down to what international standards do they have to comply with. And I go back to the TS 16949 clause, which said that the statistical studies should be undertaken, and that really is what it boils down to. But how strong are organisations at undertaking statistical studies? And that, I think, is the big question. But I think to penalise an organisation for failing a gauge R&R study is the wrong thing to do. And in regard to MAP specifically for attribute data and destructive testing, no, I've not personally come across that, but I think it is a potential minefield out in the world at the moment.
Hello, it's Roland here. I've got a question around some of the issues which Martin raised. There were a number of issues where he was talking about auditors and engineers who understood gauge R&R but have got a lack of understanding of areas such as ANOVA. How do we start addressing this as a group of statisticians?
That's something that's dear to my heart, and again, in a sense, it's a sadness that although this event today was originally advertised as a workshop within the RSS community and within the Chartered Quality Institute, that we had very little take-up, and I'm not sure what the answer is. It appears at the moment there's a lack of interest. I'm working with large corporations, I'm working with some SMEs, and I just don't think they get it. And I think a lot of organisations are only undertaking this and encountering analysis of variance because of the Six Sigma community. But I don't know what the standards are going to do, if they're going to change. And there is this movement potentially to merge TS 16949 with the ISO 9000 revision in 2015. But how can we as a society make a difference? I'm not sure. I think we need to keep petitioning the Standards Institutes, which we're trying to do from QIS committee, and we could try and influence through an initiative that Tim Davis set up, working with the other engineering institutions. But that's a long-term change of direction. The engineering faculties have always said, oh, we've got too much, we can't do any more statistics. But actually, in my mind, it's just common sense engineering. It's using statistical thinking to enable better engineers and other professions to become evident in the workplace. So what can we do as a society? I'm not sure, but I think we've made an initial start at making some changes.
If you try to do data analysis using software, of course it throws at you analysis of variance and p-values by the million. But not everyone has to understand this, and managers never will understand it. But you can communicate with managers using graphs. Perhaps you only need one person to understand ANOVA and another person who can put it all in simple graphs for managers to understand.
What are your thoughts, Carolyn, as you ask the question? Have you got any ideas?
Well, it's always a difficult one, isn't it? I mean, I think I as an individual have had similar challenges as you, Martin, and Roland as well. But as individuals, it's very hard to make a lot of progress. So, I mean, my thought is that, women webinars such as this might be potentially a way forward, because actually getting people out of the workplace these days and to a conference or to training courses can be quite challenging, really, because obviously the economic climate means that people have got to be at work and got to be seen at work, whereas taking time out for an hour or two to do a webinar, particularly over lunch, might be a good way of starting to kindle that communications. But I also think there needs to be a longer term communication plan, as it were, to get that message out there that this is an important thing to be doing. And we need to think about who we're communicating to as well, because I think often some of the people on the ground, like the technicians who are actually doing the analyses, have got quite a common sense feel for what it's about, but it's the next level up that needs to be influenced in terms of getting people proper training. But it's a difficult one. It's a really difficult one, Martin.
Maybe we could consider that the Quality Improvement Section Committee, through the RSS, actually raises our concerns and some suggestions for improvement to the industry forum, because the industry forum is although it's owned by the Society of Motor Manufacturers and Traders, which is automotive, it's actually got a much wider umbrella of companies, and they do offer training in the AIAG approaches, not only on MSA, but on things like failure motive analysis, etc. And I'm just wondering whether it could be appetite to contact them saying, are you aware of some of these issues, and do your members share these issues, and what could we do to start to change?
Yes, we could do that, and we could even have a session similar to this, just a short 1 hour session, just saying this is what we feel the issues are, and get some feedback.
Yep. So, unless there are any more questions, I thank you for everybody's participation. Roland, do you have anything else to add, or any other comments to make?
The Quality Improvement section of the RSS is planning to have either a half-day or one-day event on measurement error on Tuesday the 2nd of December.
And that will be at Errol in London?
Yes. So, if there are no further comments, is it time to close the meeting? No one is protesting. So thank you all for participating. I've enjoyed it. Hopefully it's been useful. Thank you very much.
Thank you, everybody. Bye-bye.